Okay, so this is a P5 revision video for static, and the first thing you need to know is how we can actually statically charge objects. So to understand this properly, we have to look at the structure of the material, and in particular the structure of atoms. We need to remember that everything's made up of atoms, and that in the atom we have protons and neutrons in the nucleus. The protons are positively charged and the neutrons have no charge. And the nucleus of the atom is kind of fixed in place in these materials. It can't move about at all. But we have to remember that the electrons are in shells around the nucleus. So this is some stuff from chemistry, and that generally speaking we can move the electrons around a bit. That's really important because the main way that we statically charge things, and the way that you need to be able to explain, is by friction. So I've got a blue object on the left hand side here and a green one on the right. And we've shown some of the electrons, the negative electrons, by those yellow negative signs. Obviously, there are protons in these things as well. But we're just going to show the electrons because the electrons are the things that are actually involved in moving during static charging. So what do we do? Well, you should all know this because you've all probably done it with a balloon and rubbed it against your hair and it becomes statically charged. We take the two objects, we rub them together, and then what happens is some electrons are transferred from one object to the other. Okay, now you don't need to know anything about which way round the transfer will be for any two pairs of objects. You just need to know that this happens, and that the fact that the blue object in this case has lost electrons means it's now positive, because if you think about it, it's got the protons are still there in the nuclei, and it's lost an electron that was balancing out a proton, so this blue object is now positive slightly, and corresponding the green object which gained electrons is now negative. So this works just like ionic bonding basically in chemistry, except there's the difference is the number of electrons, as we're going to see in a second. Okay? So, how does the object become charged? The steps in the description that you need to be able to write if you're asked to describe this is that we need to have the objects rubbing together, like we said. And then the proper language would be that the frictional force does work transferring electrons from one material to another. So it takes some energy to move the electrons across, and that's why we need to have the frictional force doing that work. And we need to remember that the material which gains electrons becomes slightly negatively charged, and the material which loses electrons becomes slightly positively charged. The reason we use the word slightly there is the fact that only a tiny fraction of the electrons in the material are transferred across. It's a very few compared to the total number of atoms in the material. And that's why static attraction is so weak. So it's why the force between the balloon and your hair after you've charged them up is very, very weak indeed. It's not anywhere as strong as the forces that hold the ions together in ionic bonding, because there each individual atom transfers one or two or three electrons, and here we're talking about a handful of electrons shared between millions of atoms being transferred. The other thing to note about this is that it's only very easy to charge up insulators, because if we put extra electrons on a conductor, then basically, as we're going to see in a second, they'll repel each other and they will basically flow away, and so the charge will not stay on that conductor. So we can charge up things like plastics by this frictional method, but you can't really charge up metals. Okay, so how do charge objects interact with each other? We need to know this as well. So if you have two charges that are the same, so two positive, and this would work the same for two negative charges as well, they will repel each other. So the red arrows on this diagram are showing you the forces on those charges. And the other thing that's useful to know for you as well is that, fairly obviously, if we move the objects further away from each other, those forces get weaker. And you can see that from the fact the red arrows are getting shorter here. Interesting link back to P4 is that this is, of course, an example of an interaction force pair, because we've got two objects, right, with two separate forces on the two objects pointing in opposite directions, and the forces are the same size. So this is an interaction force pair due to the electrostatic interaction. And then the other case where we have two oppositely charged objects, one positive, one negative, is that they will attract. And again, the far away the forces are quite weak. We've got relatively short arrows. If we move these two objects close together, the forces get stronger. So charges that are close together have stronger forces between them. That's a really important point for the next bit we're going to explain. So that's charged objects interacting with each other. You also need to understand why it is that any charged object, whether it's positive or negative, will attract a neutral object, so something that you haven't charged up. So what we're showing here is just an object here, and I've shown some of the protons and some of the electrons. So the nuclei here, which contain the protons, are the little yellow plus signs, and directly over the top of them, because to start with, the electrons are kind of attached to each of these nuclei, are the electrons. And what we're going to do is we're going to bring a charged object into play. So here comes the negatively charged object, and what you can see happens is the electrons are pushed away slightly from their nuclei. I'll just show you that one more time. I'll start it again. Here it comes, right? And you can see the electrons moving away. And because of what we just talked about, about the force being stronger the closer the charges are, these electrons near the surface are pushed away much more than the ones lower down. And if we showed more and more layers of these, then you'd see that the electrons on the other side of this object are barely affected. Now what this does, right, is the fact that it will basically leave a slightly more positive charge near the surface. So that makes the surface of this object slightly positive, and we've got a negatively charged object here, and we've just said positive attracts negative. So because the surface is just a little bit more positive, right, these two objects will attract. And again, if we think back to the example of the balloon, right, when you charge a balloon up with your hair, the two objects involved are your hair and the balloon. Right, they're both charged, but you can take the charged balloon and stick it to the wall. The wall hasn't been charged up, it's neutral. Right, and it's this effect that's going on. Right? The balloon will eventually fall off as the charge leaks away. So that's really important to understand, that we can always attract even more weakly a neutrally charged object. So an object with no charge that is neutral towards any charged object. If we'd replace this rod with a positive one, all that would happen is the electrons would move slightly towards the surface, and we get a slightly negative surface being attracted to the positive rod instead. So it works whichever way around you do it. Any charged object will attract a neutral object. Okay, and just another note, remember that the nuclei, the reason that they don't move is they're kind of fixed in place by the bonding in this material. Okay. Right, so we also kind of need to know how we can tell if an object is positive or negative, because you can charge the two things up, but it's kind of difficult to know whether they're positive or negative, and the only real way you can do it is by comparing to an object which you do know what the charge is. Now, because of what we've just said, right, the only real test, right, of whether we've got a positive or negative object is to try to repel it with our objects that we do know the charge of. So what I mean by that is that, of course, if you have a neutral object, then it will always be attracted. So I'm just going to put this table up and explain to you what this table means. So imagine we've got some objects that we know, one we know is positive and one we know is negative, right? And we put those known charged objects near to the thing we're trying to test. Let's say we take the positive object and we put it near something and it attracts it. Now, the conclusion we can draw from that is that it could be negative, because we know opposites attract, but we also know that neutral objects attract charged objects. So the attraction only tells us it's negative or neutral. It doesn't tell us which one. But the only situation in which we bring a positive object up to another charged object and it repels is if the unknown charged object is also positive. Okay, and the same thing works for the negative. If we have the known negative object and we bring it up to our object we're trying to test and it attracts it, that means it's positive or neutral. If it repels it, it means it's negative. So if you want a definite conclusion, right, you have to look at the repels to see whether something's positive or negative. Okay, that's quite important. Okay. The last thing we need to think about is just, it says you need to appreciate simple ideas about how static charge can cause things to happen. So I'm just going to look at a couple of examples in context, which you may not have looked at in class, but this is the sort of thing they could give you in the exam to discuss. with a little bit of context, these unfamiliar problems they give you. And you need to use the ideas of static to explain them. So I'm going to go through a couple of examples just so you've seen some, so you can think about how you would apply it if it's a different example you're given in the exam. So the first one is electrostatics used in spray painting. So if you imagine this, the blue thing on this side is a nozzle, and the yellow blobs here are paint droplets. And if you're spray painting, you probably want to have a nice even cover over the thing you're spray painting. So we're going to imagine we're spray painting onto this blue surface over here. So if we spray paint with uncharged paint droplets, they will tend to sort of stick together a little bit because they have surface tension which holds them together, and they will clump up. So if we spray the uncharged paint, the drops can clump together in flight, and we get this going on over here. If we spray them charged, though, we can have a nozzle that will either charge them by friction, or you can actually use sort of a voltage to charge them up as well. Then because all these paint droplets will have the same charge, they're going to repel each other as they fly, and they'll tend to spread out more. Okay, and you can see what the difference is between the coverage for the uncharged droplets versus the charged ones. I'm just going to list the differences. So in the case where we've got the uncharged, we've got a relatively small area covered. The coverage is lumpy and uneven. There's more droplets in some places than others. The layer might be thicker, and that means you'd need to use more paint to cover the same area. Okay. And if we look at the coverage when we charge the droplets up so that they repel each other in flight, we get a larger area covered. The coverage is more even because the droplets all spread out. We've got a thinner layer and less paint used. And the other advantage is that of course, because the droplets are charged, when they get to the surface, they will be attracted to it, even if the surface is neutral. So they should stick better to the surface, and you'll have less paint kind of wasted from not sticking to the surface. You can actually go one better than this. You can even try to charge the surface with the opposite charge to the paint, so it sticks really firmly. And sometimes they do that with things like spray painting bike frames and things like that. They can attach the bike frame to the correct terminal of a battery that's the opposite to the charge on the paint, and it will stick to it even more. Okay, so there's spray painting as one example of how electrostatics can be used. Another one is use in power stations, which kind of links back to stuff from a little bit from reducing pollution from the core part of the course, the units 1, 2 and 3. And what we've got here is something that you can put in a power station called Electrostatic Precipitator. This grey circle down here represents a smoke particle, and then we've got a metal mesh grid, right, which is connected to the negative terminal of a cell here, and then these big metal plates which are connected to the positive terminal. So what happens here is that the particle picks up charge. This is another way of statically charging things. It's not really frictional. If you have a negative potential near the object, it can pick up electrons from it, because as you'll see later on, the electrons are kind of pushed out of the negative terminal of the battery, and they will sit on this grid, and they will, because they repel each other, they will sort of jump off onto the particles as they pass. So if we look at this is what happens. The smoke particle comes to the grid, right? It becomes negatively charged at the grid, like this. And then as it moves up through the flue, because the plate is positively charged, the negatively charged particle will be attracted towards it, and it sticks. So rather than this smoke particle coming out of the top of the chimney here from the burning, it will stick to this grid, and they will gradually build up a layer of particulates on this grid that can then easily be disposed of without going out into the atmosphere. So that's static charging, how it happens, how charges interact with each other, and also a couple of uses that you can use as examples, or you may encounter in different contexts in questions.